Hello, everyone. This is Nectar speaking, and I want to tell you that I ran code from the internet, and you probably do too. Okay, so on that note, if I gave you a string of text, would you accept it and run it in your application in production without reading it? I think I know what you're answering. Would it help if I put it in a tar.gz file? I believe it would, because that's what NPM packages are. And they're great, don't get me wrong. And everyone is using them a lot, but they're actually unsanitized input from the internet that you run, aren't they, right? So we're consuming those NPM packages a lot. I know I do. What if not all of them are great? And by not great, I don't mean sloppy. I made a bunch of sloppy packages and published them, and no one complained. Nothing bad happened. What if they were actually dangerous? Right? This isn't a new problem. We have solutions for that. So there's audits. NPM audit being the one available with NPM, but there's also a lot of other possibilities, including SNCC, where you can look at your dependencies and see that, hey, there is a malicious dependency there. The thing is, the only way for those apps to know that something is there is for a researcher to find out about it and report it somewhere. So depending on the app, there's different timing and the life cycle of what is happening. So some of them are going to get the report sooner. Some of them are going to get the report later. Some of them aggregate more reports, but you're still getting a report about a dependency being malicious, because that's the case I'm after. Once you've probably already shipped it to production, that's not good enough. What are the other approaches? Well, there's a new approach where socket dev is trying to analyze things heuristically and give you warnings. But those warnings don't say, this is definitely malicious. You need to stop what you're doing and fix it. The warnings say, something happened that makes this package look potentially malicious. Now you have to research it yourself. So this narrows down the search, but you still have to do a lot of your own work. This is all reactive security. At Lavamote, we want to be proactive, not reactive. What's Lavamote? Lavamote is an open source project that is powering runtime security for MetaMask, the crypto wallet, and a bunch of other projects probably. This is open. Anyone can use it to any extent they want. So how are we being proactive? Well, I have a small demo. So let me switch to demo and show you a few things that it can do. Let's take a look at the application. There's an app.js file, which is a small Node.js application, which uses a package that we don't yet know is evil, but it actually is. And that package is used in here to get some very important content. And then that content is uploaded to a server that's being protected by authorization. And we're using a secret from environment variables for that authorization. This is how I invoke the application. I set the precious secret here, and I run node app.js, and then I also run it through Lavamote. And this is what the package is currently looking like. So there's a secret dad joke in here hidden. So this part is not yet malicious. Let's see how this develops. So I can run npm start. And what I'm also running here behind the scenes is two servers. One is the 8080 port, which is supposed to be protected by this secret to access it. And then the other one is a hacker's server, and they will show a pop-up message whenever invoked. So we know that the request went out. So when I run npm start, I'm getting a nice information pop-up with this dad joke and some output from the app. OK, now let's see what the next version of this package could look like. let's take a look at what I've implemented as the next iteration of the package. So we're requiring HTTP and making a request to the hacker port with a payload. And the payload happens to be the precious secret from process.env. What happens now if I run it? If I run it through regular node, I first get a request to the hacker server, and then I get the request that was supposed to happen. Okay, that's not good. So what does lava mode do about it? Lava mode has a step where you generate a policy first. We've generated a policy before, and the policy says that this package has access to the following globals buffer, actually the from method of the buffer, okay? And that's it. We don't have anything else in here. Now, this is using more stuff. So what happens if we run npm test, which invokes lava mode? We're going to get an error, and the error here is saying lava mode required node built-in package is not allowed on the allow list. Eval package requested HTTP. Okay, now that's blocked. Are we done? Well, let's see if the package involves any further. Now we can move on with the implementation. Is it working? Yeah. Okay. So imagine a situation where instead of having the payload built in, I fetch the dad joke that the package is returning. And then what I want to do is to also steal the secrets. Oh, I think I went too far with this. Let's see the previous iteration of that one. Yeah. Okay. So if I have access to fetch for fetching the dad joke, why don't I also use fetch to make that HTTP request, right? So if I start it, I'm going to get the secret stolen again, right? Okay, now with lava mode, we obviously had to update the policy to also allow for fetch. So if fetch is allowed, what is stopping the malicious package from stealing my precious secret? Well, lava mode. Let's take a look. What I'm getting here is an error. Node added some nice arrows to their error output, and these get truncated here. But what we're getting is an arrow pointing at env in this line, which is coming from an error saying env is on a field that we're trying to look up on undefined. Why? Because process is undefined, only for this package. So the app itself is successfully using process, but this package no longer has access to it because it's not on the allow list. That's great, right? What if we don't need to access process in any way? So I'm going to move forward with the implementation. Take a look at this. It's a bit complex to understand, but what I'm doing here is I'm using prototype poisoning. So if you take a look at the application, we're passing headers with the authorization header here, and that header goes into fetch. If I take object prototype, the prototype of the global object, and I create a setter for the authorization field, the setter is going to get invoked whenever an assignment happens to a field called authorization that didn't exist on the object itself. This is called an override mistake, by the way, and this might eventually be fixed in JavaScript itself. But this is here and works as specified in ECMAScript standard. So let's use it. If I now run this code in Node, regular way, I'm getting hacked again. And you can notice that this says bearer, %20, and then the secret, because we took the entire header and sent it to the hacker server. Okay, and that joke still works. Okay, what else can I do? Well, now let's take a look at lava moat. What is lava moat doing in this case? Well, lava moat is running under hardened JavaScript, and hardened JavaScript is protecting the built-ins of the language. So they're called intrinsics. Lava moat is protecting them using hardened JavaScript to not be tampered with. So all of the prototype poisoning options that we used to have are now gone. And this payload is not going to be usable for an attack. Okay, that's in Node.js. I can also do a similar thing in the front end. Okay, let's take a look at the front end case. This is an app. This app is being built with Webpack. This is my Webpack config, and this is a very, very early version of a score drop plugin that we intend to ship. And this is open source, so you're welcome to join us in the effort. This app is using LeftPad, a package, fairly famous. And it's also using a package called Cookie Monster that I built for this occasion. And it's giving out random quotes from the Cookie Monster, but also impersonating Cookie Monster to the point where it cannot resist any cookies available to it. So what it's going to do is it's going to grab document cookie and send it to the hacker server. Okay, let's take a look at that in the browser. We have built this in the regular way without our plugin. Without the plugin, what happens is the Cookie Monster is gonna give us a quote and then also send a request with localhost, our URL, as the path name, and then name equals chocolate chip is what we have set as the cookie. I can restart this page to see if it still works. Yep. This pop-up is from the hacker server that I'm running still. And this has been sent out. Okay, for comparison, let's take a look at the same code with the same Cookie Monster script and the same app bundle here. But this time, it was bundled with our plugin. I'm going to reload the page, and you can see that what we've sent is undefined. Why is that? Well, the Cookie Monster was looking up host on location and cookie on document. And if we look at the Webpack config here, these were not allowed. So Cookie Monster, in this part, is allowed access to fetch, math, and encode URI. We can go even further. We can deny it access to fetch, and then rebuild. Hello, okay. As you can see, this is a very early version with some random outputs. But if I now refresh the page, oh, yay, demo effect. Okay. Yeah, looks like I didn't rebuild after all. Never mind. You're going to need to believe me now that if I rebuild correctly and I have the right files in the right spots, this would prevent fetch from even being available. Okay, let's go back to the presentation and talk a bit more about what's happening there. So Let's talk about how it works. Behind the scenes, it's using hardened JavaScript, which lets us isolate each dependency within the same process, within the same context, as Node calls it, or realm as the spec calls it. How is it done? Well, hardened JavaScript consists of three functionalities: a compartment, which is a tool for scope isolation. Anything you run within a compartment is code that runs in a different global scope. You can decide what the global scope is going to be on a compartment, and you can control what it can import inside of a compartment. For that to be fully secure, you also have to get rid of the prototype pollution situation, which I demoed earlier with lava modes. And that's where lockdown comes in. Lockdown is modifying the environment in which you run, and it's using the flexibility of JavaScript to remove the flexibility of JavaScript where necessary. And this is a great idea that makes JavaScript still work in 90-something% cases. Almost anything from NPM is still going to work under lockdown, with very few exceptions where someone is trying to use prototype poisoning for good. That's in most cases where something doesn't work against lockdown. And then there's harden, which is a function similar to lockdown, but used for preventing prototype pollution or any sort of tampering with your own objects that you create in your application. So we can use that for increased security when you're passing information to something that you don't necessarily trust but want to use. Okay, and this is becoming part of the language. Eventually, it's still in its early stages, but compartments might end up in the language, I don't know, within a few years, definitely, probably sooner. Currently, there's a lot of work on module loading virtualization going on in TC39, which is a foundation on which compartments need to be built. We also have a bundler in Lava Mode, and there's a stable bundler in Lava Mode package. It's using Browserify. So if you can afford setting up your repository with Browserify, it happens to be the most flexible of the bundlers, and integrating with that was super easy. We spent a lot of time looking for ways to integrate with other bundlers to a level that would allow for applying hardened JavaScript to your packages. And this Webpack plugin is looking very good. It's still early. It's not production ready. It's barely running the demo. So if you want to help with the plugin, get in touch. We will happily get your help with that. And that means you can start using it more effectively for your own use cases. If you want to know more, there's a bunch of earlier talks about SES, which is the hardened JavaScript shim implementation we're currently using, which is fully functional with some performance trade-offs. I already did a bunch of talks around this topic earlier, and you can also look at Mark Miller's talk on F5 Tech Talks, where he explains hardened JavaScript and consequences. Much more goes into patterns and how the whole idea of using hardened JavaScript for object capability security can be introduced. Now, I also promised I'll run code from the internet, right? So let's eval something and see what happens. I'm going to switch to my other demo. Warning, this is a toy. Let's make sure you don't use it in ways where you would risk anything. This is a toy project that I made leveraging hardened JavaScript for the purpose of looking at actually malicious packages. So it starts with a shell script that runs a Docker file without access to internet, just in case something malfunctions. Now let me open it up in a terminal and show you what it does. Oops. Okay, we're going to boot it up. Oh yeah, updates. And now I'm inside of my lab environment where I can run a command called lavalab. That command is going to run the script file that we give it from samples. Okay, so I have a sample of malware called LofiGang. And this was malware that went on NPM and was trying to steal a bunch of things from people, trying to pose as a package helpful with building Discord add-ons, as far as I remember. And this is actual copy that I downloaded while it was still available. So we're making sure we're offline. And now this is not the first time I'm running this. So we're gonna use the history of the previous run where I can change my mind any step of the way, but it's going to suggest answers that worked for me previously. So let's take a look. Do I want to give it real eval? Why is it using eval? Well, I can tell you that this package, where is it? Here. This package looks like this. It's fully obfuscated. And the whole idea for the tool that we're looking at came from me trying to manually deobfuscate it. And it has 4 layers of obfuscation. And then when you go through that, it's going to go into an infinite loop if it detects that it's been deobfuscated. So I thought, I have this great tool that can help me at runtime. Why would I deobfuscate it if I can just check everything at runtime, right? So I want to give it access to eval because it needs to run obfuscated code in this case. So yes, it's reaching for a regular expression. If you didn't know, it's very common in obfuscators. So I'm going to allow this. Another layer and one more layer of obfuscation. And this is the last one. Now we've gone through the layers of obfuscation and we're setting up the actual run of the function. It's using parsin for some reason. And then this is where the actual module starts. So it wants to require FS. I'm going to go with the default of no thanks. Same with HTTPS and glob and child process. Now it's reaching for child process.exec. What do we want to give it? Let's give it a dummy function. Now it requires Axios. OK, no. Do we want to give it access to real process? No. So what should it be? We're going to return process as a general proxy. And then they're reading env proxy again. Local app data. Well, this looks familiar. Looks like someone's writing a Windows malware. OK, so let's give it a string that I can recognize later. Nice. Now it's calling read_dir_sync from fs. I'm going to give it a function. And this function is now being called with a string that I happen to recognize. So they're trying to read local app data and then probably iterate over it. My tool is not yet developed to the extent where I could run this for each with some interesting data that it would collect and then want to report on. So we're going to miss out on that part. But let's move on to the next part that it's doing. It's calling child process exec on task list. That's looking up active processes. So they are collecting info on what to hack later. Interesting, isn't it? OK, and the last bit is it's reaching for the post field on Axios. Let's give it a function. And then it's calling the function with a Discord webhooks address. So it looks like the malicious actor building this thing is using Discord webhooks for sending stuff to a Discord channel somewhere as their sink for data. At least that's my speculation. And I got all of that without ever deobfuscating any of the code. That was fun. Okay, last but not least, Lava Mode is a nice project. It deserves more adoption. So if you see this and you have a project where a package JSON is present and it has some JavaScript, I offer help to set up Lava Mode for your project that you're building for work or in open source, somewhere where people can use it. I'm going to help you out with Lava Mode so that you can secure your project in exchange for a bit of feedback. Thank you, everyone. I think that's it. I can reiterate my failed demo later, or you can try it out yourself. It's in the repository. You can go to nuptor.pl and then look up the presentation, look up my GitHub account. Everything's there. Thanks for your attention, and stay safe.